In this video, we are going to review how to compose a trig function with an inverse trig function. So I've tried to put a good variety of examples here. And in fact, for each of these examples, I'll give you follow-up questions so that you can practice kind of doing extra computations on your own. My goal with all of the examples that we look at today, how we set up and solve these problems, is to strengthen your understanding of geometry. So instead of just cranking this computation out in a calculator or something like that, I want you to really understand what arctan is saying and then how to take the knowledge we get from the arctan expression on the inside here and evaluate cosine on that innermost expression. Okay, that will make more sense as we work through it. Let's start with this first example. Before we actually compute the cosine of the arctan of 3/2, let's take a moment just to revisit SOHCAHTOA. You might be completely familiar with this expression and how to evaluate sine, cosine, and tangent of, say, this angle theta, but I think it's worth just stating a few facts about trig out loud because it will help you understand what the inverse trig functions are doing. So for this angle theta, if I compute the sine of it, the result is a number that reflects the ratio of the opposite side to the hypotenuse. For cosine, the cosine of this angle is the ratio of the adjacent side to the hypotenuse, and tangent is the ratio of the opposite side to the adjacent side. That's probably familiar. So reflect upon this though. What sine, cosine, and tangent do is they take in this angle and return back a ratio of sides. Similarly, if I take 1 over sine, 1 over cosine, 1 over tangent to get cosecant, secant, and cotangent, because I did throw those functions into our examples for today, inverting a ratio is still a ratio. So cosecant would be the ratio of the hypotenuse to the opposite side, secant, hypotenuse to adjacent, I'm trying to say everything backwards here, and cotangent would be the ratio of the adjacent side to the opposite side. So sine, cosine, tangent, and their reciprocals, cosecant, secant, and cotangent, take in angles and return you back ratios of sides. The inverse trig functions behave in the inverted way. So an inverse trig function, like arcsine, takes in a number and returns you back an angle. Now, what we're going to do in all of our examples is really understand how to read what we're plugging into, say, arcsine, like how to do that backwards process. But when you look at, let me take the expression that we'll see first, arctan of 3/2. When I see this expression, what I want to do is think of this as the ratio of the opposite side to the adjacent side. So this is a ratio of sides, and what it's returning me is an angle. We are then going to turn around and take that angle and plug it into cosine. So it's like we'll interpret this as a ratio of sides. This will give us a way to label the sides. Then we'll say, okay, here's the triangle that matches our inverse trig description here, and then we'll plug that into one of our standard trig functions. So at this point, what I really wanted to emphasize before we look at our first example is your standard trig functions take you from an angle to a ratio of sides, whereas the inverse trig functions take you from a ratio of sides, that's what we're plugging in, to an angle. Okay, let's see how that works now for cosine of arctan of 3/2. It shouldn't surprise you, if you're familiar with my general approaches to solving problems in life, that we are going to work off of a triangle because I really believe in bringing in the geometric ideas as much as possible. So all of the examples that we are going to work through are going to be on essentially this triangle, possibly rotated or reflected. It does not matter what the side lengths of this triangle are or what this angle is, whether it should be 20 degrees or 70 degrees, that doesn't matter. When you draw a right triangle to evaluate this kind of computation, you just need to ensure that the hypotenuse of your right triangle is pointing into the correct quadrant. So the first three examples, we are going to be taking a trig function of an arc trig of a positive ratio of sides. When you have a positive innermost input, draw your hypotenuse so that your right triangle is situated in the first quadrant. So imagine that this is the origin, this is the x-axis, right here is the y-axis. My hypotenuse is like a ray pointing into the first quadrant. So for our first three examples, we will use this triangle, and we won't adjust it for different quantities because it just has to model the geometry of the situation. The lengths and angles don't have to be perfect, so long as your right angle is indeed a right angle. Okay, So we have a triangle whose hypotenuse is pointing into the first quadrant. We're ready to go. So how do we read this? We have cosine of an arctan value. What this inside arctan expression is returning us as an output is an angle theta. It's the angle theta in the first quadrant, so between 0 and pi over 2, whose tangent value, let me write theta so that tan of theta is this number 3/2. It's like tan of theta is 3/2. Take the inverse tan of each side, you would get theta equals arctan of 3/2. Given that tangent of this angle theta is 3/2, I can now label the opposite and adjacent sides of my right triangle using SOHCAHTOA. So here we have OA. All right, so the opposite side is 3. The adjacent side is 2. Pythagorean theorem will tell us the length of the hypotenuse. So it's going to be the square root of 2 squared plus 3 squared. So that's square root of 4 plus 9, which is square root of 13. We've now labeled all of the sides of a right triangle, and we're being asked at this point to compute cosine of this angle. So that's all this inside is. It's an angle, and we're now doing the cosine of it, but we know exactly what that is because we can read it off of this right triangle. So the cosine of this theta is adjacent over hypotenuse. It's 2 over the square root of 13. That's it. That's really all there is to doing this kind of computation, is just set up the triangle, figure out the 3 sides, and then do SOHCAHTOA back. All right, let's now compute the sine of arctan of 3/2. So give you a moment. So what is the sine of arctan of 3/2? It would be opposite over hypotenuse, so it would be 3 over the square root of 13. And sticking to just the triangle for a moment, let's do the tangent of arctan of 3/2. Well, you would look at this and say, okay, that's opposite over adjacent, so that's 3/2. And then you realize that tan and arctan cancel each other out. They're inverse functions. So it shouldn't be a surprise that we get back 3/2. If you wanted to, you could keep going because, again, I did bring in the sort of less typical trig functions. So secant of arctan of 3/2 would be 1 over the cosine value, so that would be square root of 13 over 2, and you could do cosecant and cotangent similarly. All right, that's it. So let's do 2 more examples where this inside ratio of sides is positive. So the triangle will look the same each time. For our first 3 examples, it will be a triangle whose hypotenuse is pointing into the first quadrant. And then just to be really thorough, I will negate the inside and we'll see what to do in that situation. So how to adjust our triangle picture. For our second example, we are going to compute the tangent of the arcsecant of 4/3. Again, 4/3 is positive, so I'm going to stick with the same triangular configuration from a moment ago. Our hypotenuse here is a ray in the first quadrant of the xy plane. Once again, arcsecant is an inverse trig function. So 4/3 is something that we want to interpret as a ratio, and the result of computing arcsecant of 4/3 is an angle value. It's the angle so that the secant of that angle is 4/3. I don't like secant if I can switch to sine, cosine, or tangent. So what is secant? It's 1 over cosine. So if I flip both the left and right-hand sides of this equality, we'll get cosine of theta is 3/4. In other words, cos, so this is adjacent side, hypotenuse. If you're very comfortable with secant, you might have just said, hey, that's the ratio of the hypotenuse to the adjacent side. Okay, so let's see, I've got a lot written down here, but it should all agree. So the adjacent side is 3. The hypotenuse of this triangle is 4. That means that the opposite side is the square root of 4 squared minus 3 squared. So 16 minus 9 leaves us with square root of 7 for the opposite side. And again, at this point, we're actually done. There's really nothing else to do once we've evaluated or once we've set up the 3 sides of this right triangle. We can immediately say what the tangent of this angle is, because this angle is the same angle that we sketched here. We know this because the cosine of this angle is 3/4. Okay. So tangent of this angle is opposite over adjacent. That's square root of 7 over 3. Take a moment to write down sine and cosine of arcsecant of 4/3. There's really not very much work left to do if we want to evaluate the cosine and sine of the arcsecant of 4/3. So in particular, the sine of theta for this angle is square root of 7 over 4, which means that sine of arcsecant of 4/3 is square root of 7 over 4. And similarly, the cosine of the arcsecant of 4/3 is 3/4. And that's really it. So let's move on to our next example. Our third and final example, where we are working with a positive ratio of sides on the inside, is the cotangent of arccosecant of 5. I'm really bringing out every trig function here because I want you to have a lot of confidence by the time you finish this video. So if I only worked with sine, cosine, and tangent, I feel like that leaves a little bit of uncertainty that you don't know how to generalize it beyond that. But I want to emphasize here that all 6 trig functions and their inverse functions can be interpreted in this language of angles and ratios of sides. So take this exercise as far as you can. I'll come back in a moment and give you a hint if you're struggling to get started, but really try to see if you can get all the way through to the final answer. As promised, a quick hint. If you saw this number 5 and were stumped because it didn't look like a ratio, remember that you can always take a number and divide it by 1. So if it helps, think of 5 as 5 over 1, and I'll give you a few more moments to pause and see if you can take this problem as far as you can. We want to do the cotangent of the arccosecant of 5. Although those functions are not as familiar as our famous trig functions, it's going to follow the same process. So the first thing I'm going to do is look at the inside and recognize that the arccosecant of 5 over 1 is the angle theta in the first quadrant, whose cosecant is 5 over 1. So theta, so that cosecant of theta is 5 over 1. And again, if it helps, you can flip both sides. 1 over cosecant of theta is sine of theta. And flipping this gives us 1 over 5. All right, if this is the angle theta, then what we want to do now is label the opposite and hypotenuse sides with 1 and 5. Like so. Pythagorean theorem gives us that this side is the square root of 25 minus 1. That's 24, but I'll simplify that a little bit. 24 is 4 times the square root of 6. 4 is a perfect square, so we can write this as 2 times the square root of 6. Mentioning that because I'm noticing just a little increase in uncertainty when I'm in conversation with students about how to handle square root expressions. So just wanted to show that to you. And now we are ready. So cotangent is 1 over tangent. That means, maybe it's helpful to write out here that if tangent is OA, O over A, then cotangent is AO, A over O. Okay. I do not say the backwards direction quite as quickly as the forwards direction, but that's what we're looking for. Adjacent over opposite is 2 square root of 6 over 1. That's the ratio of sides, but it might be simpler to write that as 2 square root of 6. What's our sine, cosine, and tangent of arccosecant of 5? You can read them right off of this triangle. Do that, and I'll come back in just a moment. If I wanted to know the sine of the arccosecant of 5, I would do opposite over hypotenuse for this triangle, labeled this way, so that would be 1/5. For cosine, it would be 2 square root of 6 over 5. And for tangent, it would be 1 over 2 square root of 6. All right, I hope that resolves any situation you may have encountered where the inside ratio was positive. The triangle is always going to look like this. Let's switch now to 3 examples where this inside ratio is a negative number, because when it is, we have to be a little bit careful. The ray that we're going to draw should either be in the second quadrant or the fourth quadrant. So our triangle is either going to flip like this, flip like this or flip like that. Let me outline first when each of the scenarios occurs. For the 3 examples that we were just looking at, the interior ratio of sides was positive, which meant that we sketched a right triangle whose hypotenuse formed a ray in the first quadrant. So it's like we imagine the hypotenuse is like this, drop an altitude straight down, and that gives us the proper configuration for our right triangle. What do we do if the interior ratio of sides is negative? Let me give you the quick answer, and then I'll give you the long answer, depending on whether or not you would really like to understand more about why it's the case. So the quick answer is that if the interior inverse trig is arccosine or arcsecant, that pairing, if the ratio of sides is negative, sketch your right triangle so that the hypotenuse is a ray in the second quadrant. If it's arcsine or arccosecant, that pairing, draw the hypotenuse as a ray down in the fourth quadrant. So it's like for arccosine, arcsecant, you're here. Arcsine, arccosecant, you're here in the fourth quadrant. What about tangent and cotangent, or rather the inverse functions for those? It's actually a little bit tricky. For arctangent, you are also down in the fourth quadrant. But for arccotangent, you're in the second quadrant. So to summarize, arccosine, arcsecant, arccotangent are here. Arcsine, arccosecant, arctangent are here. Wow, I really hope I said all 6 of those correctly. I'll say it one more time. Arccosine, arcsecant, arccotangent, arcsine, arccosecant, arctangent. Okay, I think I got it correct that time. It's just a lot of trig names. Why is that the case? Let me just give you a quick, longer explanation. If you want to invert cosine, well, you can't invert it as a function from r to the closed bounded interval from -1 to 1 because it's a wave, so it doesn't pass the horizontal line test. But what we do is we say, well, how does the cosine function behave on angles from 0 rotating counterclockwise through pi? If you do that and you track the cosine values on that half arc, what you'll find is that cosine starts at 1, decreases down to 0, and then decreases down to -1. That's one full range for cosine. So if you just restrict your attention to that set of angles, then cosine is invertible. So that's where we define arccosine. And then I don't want to get too much into arcsecant, namely how things behave on the axes, but in the second quadrant, you can do 1 over cosine to get secant, and you can also do arcsecant there. Okay. Compare that with sine. If I consider the same set of angles for sine, what does the sine function do? Well, it starts at 0, it increases up to 1, but then it decreases back down to 0. So sine is not invertible if we just restrict our attention to angles between 0 and pi. So how we treat sine is we look at angles from -pi/2 up through 0 up to pi/2. On that particular set of angles, sine starts at -1, increases up to 0, and increases up to 1. So for that angle restriction, we get one full set of output values for sine. That's where we invert sine. And again, similarly, we get arcsine there. We also get arccosecant, arccosecant. For tangent, if you just think about like one branch of the tangent function, one smooth branch of the tangent function goes from -pi/2 to pi/2. So just like for sine, tangent is defined strictly between -pi/2 and pi/2, where tangent, we don't define it right at -pi/2 because that would be kind of like it's trending to -infinity, at least from the right. But anyway, so it's very negative numbers up through 0, up through very positive numbers trending to infinity. So that's the natural place to invert tangent, which means when we look at arctan of negative numbers, we're down here in the fourth quadrant. But notice that we went through 0. If we invert that, it gets to be a problem. So how we fix that with arccotangent is we have it in the first and second quadrants. Okay. All right, so that's 6. Let's see, it's, I guess, a total of 12 functions if you put it all together. So I hope I said it correctly. We will now do 3 examples where I believe I left off arccotangent. That's kind of the outlier for the general classification system that we just went through. But just keep in mind that arccotangent, if the ratio that you're plugging into that is negative, you would be in the second quadrant. That might be a surprise if you keep in mind that arctangent would be down in the fourth quadrant. For the rest of them, we want to follow this like general way of situating our triangles. We have to do it carefully so that our triangles are either correctly in the second or fourth quadrant, or rather the hypotenuse that we sketch is a ray pointing in the correct quadrant. And then also as we label the sides, some of the sides might be negative. So you have to be careful with picking the correct configuration and also labeling your sides carefully, but I'll show you how to do that with our first example. Let's evaluate cosine of arctan of -1/4. That puts us in the fourth quadrant as we just discussed. So here you want to imagine that this is where the origin is located. This is like the x-axis. This is the y-axis, not sketched here. And the hypotenuse is like a ray pointing down into the fourth quadrant. Okay, that's the correct positioning for the triangle. You have to be a little bit careful when you label because we have to put a negative somewhere. And let me just go ahead and tell you not to put it on the hypotenuse. A little bit more detailed explanation is you want to think of labeling these sides as labeling the correct x and y coordinates. So if we're down in the fourth quadrant, it's like the x coordinate will be positive. This side will get a positive number. The y coordinate down in the fourth quadrant is negative. So we will put a negative value here. And then for the hypotenuse, think of that like a radius. It's always going to be positive. Okay, so we have arctan of -1/4. That means that this inside is an angle theta so that I was trying to write so that, but then I started to write tan. So that tan of theta is -1/4. That's opposite over adjacent. Okay, let's label that on our triangle. Here's the angle theta. The opposite side is going to be -1, and the adjacent side will be 4. And again, you want the side labeling to have to be positive or negative in agreement with whether or not the x and y coordinates down here are positive or negative. So x coordinate, we're on the positive x-axis. Here's the origin. So x is positive over here. Here's the origin, so y is negative. That's why this is negative and this is positive. And then the hypotenuse is going to be the square root of 16. 4 squared is 16 plus 1, so square root of 17. Okay, so that is the hypotenuse. We can now immediately do the cosine of that. So it's going to be adjacent over hypotenuse. It's 4 square root of 17. Quick exercise for you before I come back and reveal the answers. Hopefully we agree. What are sine and tangent of arctan of -1/4? And then if you like, let's also do cosecant. All right, sine of arctan of -1/4 will be opposite over hypotenuse, so that's -1 over the square root of 17. Tangent will be opposite over adjacent, that's -1/4. Look how that canceled out. Tan of arctan of -1/4 is -1/4. And then I can't remember what I said. Cosecant. Cosecant of arctan of -1/4 is going to be 1 over sine. So that's hypotenuse over opposite. Unless I've gotten turned around, that's square root of 17 over -1, so it's negative square root of 17. Okay, let's move on now to another example. I'm going to put it up and have you solve as much as you can. I didn't change the -1/4 for this example, but the triangle will be different. So we are going to do tan of arcsine of -1/4. Take a moment to pause and label this triangle. Probably I should have given you a moment to identify that the triangle should point down into the fourth quadrant, but that is the case. So I've done that first step. Label the sides and then see if you can get tangent of arcsine of -1/4. And go ahead and do cosine and sine as well. On this triangle, oriented this way, we want to label the sides of this triangle so that sine of theta is -1/4. That's opposite over hypotenuse. And again, that tells us how to label the sides in terms of whether or not they are positive or negative. So just like before, same rationale, this is going to be negative. Y coordinate in the fourth quadrant is negative. Hypotenuse will be positive. And then the adjacent side will also be positive because we are on the positive x-axis if this is the origin. So that's going to be the square root of 16 minus 1 square root of 15. Let me emphasize here that it was the square root of 4 squared minus -1 squared, which is +1. I just didn't want the -1 to get confusing there because here I'm getting a side, so it's hypotenuse squared minus the opposite side squared. Okay, so that's why that's square root of 15. We can now say what the tangent of this angle theta is based on this labeling. It's opposite over adjacent, so that's -1 over the square root of 15. Sine of theta will be -1 over a fourth, that's no surprise. And then cosine of theta will be square root of 15 over 4. Secant of theta would be 4 over the square root of 15, etc. Okay, let's wrap up with one more example. I realized I wanted to give you the first step. So this is our last example. It's cosecant of arcsecant of -9/5. So actually, before I put up my triangle, go ahead and pause and sketch the right triangle. So do that right triangle diagram and then see if you can label the sides. The process again is the same. We just have to be careful that the triangle is situated in the correct configuration and that we label the sides carefully so that the negative makes sense. For cosecant of arcsecant of -9/5, I sketched a triangle in the second quadrant. I hope you did as well. In this particular configuration, this is where the origin is located. This is the x-axis. Values along this side of the x-axis are negative, whereas the y-axis, not pictured, is positive. And we want to imagine that the hypotenuse of this right triangle is like a ray extending into the second quadrant. So what is the inside expression here doing? Arcsecant of -9/5 means we want to think of this angle theta as satisfying, so this is theta, such that secant of theta is -9/5. And again, if it helps to invert it, or rather I should say flip it, so just take the reciprocal of each side, 1 over secant of theta is cosine of theta, and this flips to -5 over 9. Okay, so with that information, we can fully label the sides of this right triangle. Cosine is adjacent over hypotenuse. Let me just write 5 and 9 for now. We have 5 for the adjacent side and 9 for the hypotenuse. Where's the negative going to go? Because we want to have -5 over 9. Goes down here. Hypotenuse, always positive. Here, the x-axis is negative because we're looking to the left of the origin. Everything should always be consistent. So the negative should kind of feel right after you've labeled it. And then what do we have here for the opposite side? Oh no, that's going to be square root of 81 minus 25, 60, square root of 56. That's fine. 56 is 7 times 8, or perhaps it's better to think of that as 14 times 4. So that's 2 square root of 14. Doing a lot of mental math here. I didn't really expect. I wouldn't have picked 9 if I had. Okay, anyway, so that's the sides. That's the third side of this right triangle. Now if I want to do cosecant of this angle, because really what we have inside now is the angle over there in the bottom right of our triangle graphic. So we can do cosecant rather of this angle by just reading off the correct ratio of sides. Cosecant is 1 over sine. Sine is opposite over hypotenuse, so we need this to be hypotenuse over opposite. So that's going to be 9 over 2 square root of 14. Okay, and what would sine of arcsecant of -9/5 be? That would be opposite over hypotenuse, so that would be 2 square root of 14 over 9. What about tangent of arcsecant of -9/5? To figure out tangent, it would be 2 square root of 14 over -5. Okay, I think that's enough examples. So we did 6. And I hope that this video did 2 things for you, really. So one is to become more comfortable when you see trig of arctrig. In fact, not only to become more comfortable, but I think it's kind of fun once you see how to do it this way. Secondly, I really hope that over the course of these examples, you now feel more confident, not only dealing with inverse trig, but also just regular trig. So I think that trigonometry is a stumbling block for a lot of people. And the more you kind of sketch supporting diagrams, so if you're working with your basic trig functions, go back to the triangle when possible or when you would find it helpful. And I hope that now, having worked through these 6 examples, that gives you a better sense of how to do that. Okay, I'll wrap it up there. Thank you for your attention.